Right. So this, I mean, a lot of these things should be applicable to multiple tasks, as I also like to claim in papers, but we'll see. Most of the things are mainly for segmentation, though. And this is kind of the list of things that we are going to go through. So let's start. And this is really for people who, are basically dealing with medical data for the first time, or things like this. So for most people here, this might be all things that you already know, but we thought it would just be nice to have everything in one place. Right. So one thing that kind of people have to get used to a bit if they're coming new to medical imaging is that data is in different formats. So typically we have NIFTY or DICOM, but there are also some less common formats. And yeah, we just have to get used to how to read and write data from these formats. And one thing to note is that in medical images, you usually have intensity values, of course, for each pixel, but you also have this meta information. So you will have, things like resolution, field of view, scanner information, acquisition information, and so on. And it's good to know how to read and write these things also. The next thing is basically also getting familiar with the data in terms of how it looks. So there are a number of these viewers. And I think if someone is new, then it really helps to, just get a feel of the data by looking at it, scrolling through these 3D stacks of slices and so on. Also, if you're looking at segmentation, then it's nice to overlay images and segmentations to play around with the, the color maps. Yeah, just to know what kind of data you're dealing with, what are the intensity ranges, if there are some patterns. To the next slide. Maybe this slide is not good. Yeah, the next thing is once we know how the data looks like, we want to look at it as numbers. So these libraries are there for they provide nice functions that we can just stick in the path of the image, and then they spit out the data that the image contains. And here are some links for how to use these functions, how the IO looks like. Right. And once we have these arrays of numbers, then I think it's useful to maybe plot histograms or just print the intensity values, the ranges at least, or the percentiles and so on. And since we are only working with, tens or maybe a few hundreds of images, maybe we can even do this for all the volumes that we have at hand and get a histogram over for example, the minimum value over all the volumes that we have, or something like this. I guess it's somehow useful while debugging later if a particular image just stands out or something like that. Also, but I guess it's worth noting that the pre-processing pipeline that we will discuss later will likely remove a lot of these differences, but yeah, and therefore it might be useful to repeat this kind of analysis after the pre-processing pipeline as well. Right. Yeah, I think it's quite useful to write some very small functions to visualize simple data, images, labels, and so on. I think it's recording. I don't know. I did say record on this computer, and it shows me pause recording and stop recording. So I guess it's recording. Right. Yeah, visualization is useful. Yeah, we have had instances earlier where a lot of trouble could have been saved if we just visualized images and labels at an early stage. So please, if you're new to medical imaging, then please invest some time. I mean, this is not going to take a lot of time, just matplotlib.im show or something like that, but do save images more often than you think is necessary, just to be on the safe side. Also pay attention to kind of rotation of volumes and so on. So CNNs are not rotation invariant, as we know. So if your data sets are not oriented in the same way, so if I'm looking at an image of a brain, it should always be like this. But if
somehow it's rotated by 90 degrees, you may want to just, rotate it back as a pre-processing step and not have the CNN worry about that. Then also you will have noisy data sets quite often. So, if you're having two data sets, one from Zurich, one from somewhere else, the person who labeled data here might have called the prostate central zone as 1 and the peripheral zone as 2, and the other guy would have done the opposite. So check for things like that. Also, the directory structure is quite important. In the end, you will end up having, I don't know, 50 to 100 experiment settings, and then it becomes quite difficult to know which results correspond to which setting. And I don't know, I don't have a good solution for doing this. I end up having typically path lengths that are 100 to 150 characters, which is not very easy to read, I guess. But yeah, so if there are any solutions for this, I would be happy to know that. But in any case, you should have something. You don't want to do this very arbitrarily. Right. So that's about the familiarity with data. The next is preparation. So we are in medical imaging. So we don't, unfortunately, we don't have, kind of ready-made data sets with training, test, and validation splits. So we have to do that ourselves. And I think we need to pay a bit of attention as to how exactly we do this. So, okay, the training set is to minimize the training loss function. We are mostly talking about supervised learning here. But in any case, okay, we will have some kind of optimization going on. And the main loss function that we optimize, that should be done on the training data set. The validation data set is used for selecting any hyperparameters. And generally what people think of this is, learning rate, stopping criterion, so which iteration to stop at, and so on. But it's important to note that it's also whatever modeling choices you make in your method development. These are also hyperparameters of your method, right? For example, if I'm deciding whether I want to use the L1 or the L2 loss, I should try them both out and then compute the performance on the validation set and select the one with the better loss. Something like that. I don't want to use the test set for making this decision, because if I do that, then the test set has become the validation set, right? So I don't want to use the test set to influence my method development. Ideally, I would use my test set only, 2 hours before submitting the paper. But, we all know how that works, but, right. Then how many images to put in training validation test? 60, 15, 25, 60, 20, 20. These sound like good rules of thumb. And one way, like kind of in detail to do this is if I choose 60, 15, 25, then I should first split 75 and 25 for training and test. And then in the training, I can do something like cross-validation. So I can make multiple folds and use like all but one fold for training and the other one for validation. And then for selecting these hyperparameters that we talked about before, I can use the average performance on all the different folds. And once I have finalized my method, then I go ahead and evaluate it on the test data. Right. And if my data has certain groups, meaning if I have, let's say, 100 images and only 20 of them are, unhealthy and the 80 of them are healthy, then I want to divide healthy and unhealthy images equally amongst my training, validation, and test splits. I don't want to train on only healthy images and then test on unhealthy images, right? But beyond this, I want to make the splits randomly. That is, I don't want to make any biases in one of the sets, because that's not going to end well. Right. And then if my data set is big enough, then I can do this entire process only once. But if I have, I don't know, only 10 or 20 images, then my test set will be only 4 or 5 images, which is not going to be sufficient for getting kind of for me being confident in my results. So what I can do is I can repeat this process here multiple times. So I can do this 75-25 split randomly 3-4 times, and then average, and then report average results over all those splits. And this also has to check that if I do multiple splits amongst at this level, and then if I get consistent performance on the different test sets, it shows me that my method does not depend very much on a particular training set. And that's also a nice thing. Right. Then pre-processing. Yeah, so the first thing that I have here is skull stripping. So if I have brain images, usually the skull is not of a lot of interest. So I would, and it tends to influence performance, I hear. So basically what people do is just get rid of it before doing further processing. And there are like dedicated algorithms for doing this, but if we are doing segmentation and we have labels for each pixel, then we can just use this. Like if you know where the skull pixels are, we just use that to set those pixels to the background intensity. The next step in MRI is to do this bias field correction. For people that don't know about bias fields, what happens is this due to the acquisition process, what you're going to have is a smoothly varying multiplicative noise. So the same tissue, so in this case, the white matter, is going to look a bit darker here than here, right? And if you're then trying to segment white matter, you don't want the network to have to remember something like the white matter in the top left is of smaller intensity than the white matter in the bottom right or something like that. You want to take away this positional artifact essentially. And there are kind of established algorithms for doing this. So in my experience, it's always nice to, if you know that something works very nicely, then just throw it as a pre-processing step and get rid of artifacts as much as possible. So there's this N4 algorithm, which, let me see if this works. Yeah. So basically there's this executable file on the, in one of the shared servers. And then you just need to give it the input and the output file paths, and it's going to take the image with the bias field and going to throw out the bias field corrected image. Yeah, and it takes about, I don't know, 15 to 60 seconds on a GPU, on a CPU, as far as I remember. Right. The next step is to match the spatial resolutions. So again, CNNs are not rotation invariant. They're also not scale invariant. So, one way to deal with images of different scale would be to have a data set that contains many different scales. But the other way would be to remove all kind of scale differences. And a way to do this would be to rescale images. For images, we can use bilinear interpolation or bicubic interpolation. And for labels, because these are discrete values, we should use nearest neighbor interpolation. Generally, what we do is we work with 2D CNNs, even though our data is 3D. And what happens is the resolution is typically sparser in one of the directions. So what we do is we use the dimension with better resolution as the 2D slices that get fed to the CNN. And we also do the resolution matching in this direction, right? For example, in the prostate data set, I think in the actual dimension, you have 0.65 times 0.65 millimeters. That's the size of each pixel. But in the other direction, the through volume direction, you have like 5 centimeters or something like that, or 5 millimeters. 5 centimeters would be too much, 5 millimeters. So that's much less resolution there. So we don't want to interpolate through that much tissue, but we do it through the slice that gets fed to the CNN. A point to note here is that I was always using this rescale function from the SK image transform package. And this behaved a bit weirdly for particular rescaling factors. So sometimes I would have, for example, the prostate in the original image, and then I would rescale it by a bit, and the prostate would go away, right? So there was something weird going on. And for other rescaling factors, it was working fine. I don't exactly know the reason for this. So yeah, as we said before, the pre-processing pipeline it's good to check what happens before and after the pre-processing pipeline, just to make sure that you're not doing something you don't want to do. Right. The next step is to normalize the intensities. So you can either do it over the data set. So you can compute for each pixel the mean and standard deviation values over all your training volumes and then normalize with that. Or you can do it for each volume. So for each volume, you can compute the mean and standard deviation over all the pixels and then normalize with that. Or you can do it. Okay, so the first two are called standardization, when you subtract the mean and divide with the standard deviation. And if the other way to do it is what is known as normalization, where you subtract the minimum value and divide by the range. And if you want to be a bit robust to outliers, then you can use some percentiles instead of the min and the max values. And I think I always use this, and this seems to work okay. So, but I also see in papers people using the other one. So I'm not so sure if this ends up affecting performance so much at the end, but just select one. If you're doing image-wise standardization or normalization, do not do it for each 2D slice, because you don't want, for example, the same structure in different slices of the same subject to have different intensity values. Okay. And then finally, what you want to do is you want to make all these 2D slices of the same size in terms of the number of pixels. And you should do it after you have done the rescaling. Right. And this is helpful for, just makes the IO easier in the training loop and so on. Right. And this is again the point about visualization, that you want to look at these images before and after the pipeline. And the other thing is you may want to look at histograms of training and test images and check if they have kind of a reasonable overlap. Because if not, then there might be this domain shift issue where your performance might be reduced. Yeah, and then once you have pre-processed all this, then you may want to save all these images, labels, all the metadata and so on in one file. This again simplifies the IO during training. And HDF5 is a good file format for dealing with such kind of varied data. And also it helps. I think it is also nice for saving like large data. Right. So now with that, let me hand this over to Krishna, who will go through the rest. You want to come here?
So yeah, next we will continue with the network details. So UNIT is the most widely used network architecture for medical image segmentation. You can have both 2D and 3D units. And what we have observed is they work quite well on most data sets. So as you can see, they have like a contracting and expansive paths, and these skip connections play an important role in getting good performance. But like I said, there are other architecture choices, like there are different kind of network architectures from ResNets, DenseNets, attention-based units, and transformers recently. And the choice of this architecture can affect the final performance which you get on a given data set. We have done reasonable evaluation on these different architectures, but of course, this is limited to only some data sets which we were able to evaluate. And we have seen that like the 2D networks perform as well as 3D networks, provided you do a good hyperparameter search and include all kinds of data augmentation in the training. And also secondly, we have also seen that attention blocks and transformer networks were not able to provide significant gains over these 2D CNNs. But like I said, you might have to figure out different hyperparameters maybe for these transformer networks and try to get the optimal performance. So one research direction is to find this optimal architecture for a given data set, and AutoML is one step in this direction, but still a lot of research has to be done in this direction to be able to figure out what's the best kind of blocks and the architecture which we can use for a given data set. Coming to network initialization, I think right now, currently, everyone uses the right set of initialization, but previously there was a lot of debate on what kind of weight initialization should be taken into account, because this is quite crucial for the network training and stability and convergence point of view. So we do not want to assign any of these weights with 0, small or large or random values. And it has been shown that this can lead to slow learning or divergence, and also in some cases causes exploding or vanishing gradients. So the two popular initializations are this He's initialization and Javier's initialization. And for ReLU activations, which we use mostly in this image segmentation blocks, we use this He's initialization. And the next important factor is this batch norm. And it has been shown that, and we have also practically seen that using batch norm improves the training. In that sense, I mean, the convergence is faster and there is less stability issues. And with this, you could also use higher learning rates. And one thing to note with respect to this, how this batch norm parameters are updated, is that during training, you aggregate them throughout the training, but at test time, you use all the aggregated parameters which you built across in the training. And you don't want to update these parameters at the test time based on the local batch statistics. And secondly, you also have activation functions after these batch norm layers. And generally, ReLU is like the most popular choice for segmentation. And one thing to note is in the last layer, you do not want to have any batch norm or any such activation function. Usually the convolutional layer output is followed by a softmax layer. And in this softmax layer, you have like the C channel outputs, which correspond to your C classes, which you want to segment. And another important block in this expanding path, or the decoder you can call, are these checkerboard artifacts, which you observe when you use this deconvolutions. So as you can see in these images on the left-hand side, you see with deconvolution layers, it creates this checkerboard artifacts, and you can reduce that by using two options. One is using upsampling layers, or you could use kernel size, which is divisible by the stride of the kernel. Next, we will see some training details. So the typical loss functions which we use are like cross entropy loss, and for imbalanced data sets, one could use dice loss, weighted cross entropy, and focal loss. And we have seen that dice loss works quite well on most data sets. And some articles also suggest that combining both the cross entropy and dice loss does better than using one of them. And for evaluation metrics, we have dice score, average surface distance, Hausdorff distance. And when you are reporting these values, ideally you should not consider the background class. And coming to regularization, like this is quite helpful, especially when you're training with limited data as such. So the popular regularization techniques include this L1 and L2 norm, which you apply on the weights. And the second one is the dropout, which also helps in this regularization. And one thing to note here is that basically with the dropout, you switch off some neurons in the training. So the output does not have the same scaling factor as you would observe at the test time. So what you want to do to counter this is you want to scale up the final output logits by this factor of 1 minus P. P is the probability of dropout here. So, but in classification and segmentation, since you use a sigmoid or softmax layer at the last, even if you don't do this, somehow it helps you not get into problems, but this might affect your performance, especially for a regression based task. And at test time, as we know, like we set this value to 0, which equates to all the neurons being enabled at the test time. And coming to optimizers and learning rates, we do not use SGD based optimization. We use some momentum based optimization for most of them. And the popular choice is like this Adam optimizer. and with the learning rate of 10 power minus 3. And when you try to change this learning rate, try to be cautious about you setting the right beta 1 and beta 2 parameters, which are associated with this ADAM optimizer. And like I said, like this learning rate is also dependent on the data set, and 10 power minus 3 is a good value to start with. And like if you are using an SGD based optimizer, you want to decay the learning rate, and generally the decay factor is by 10, the factor of by 10, and you do this periodically after every few number of epochs. And in ADAM, this rate decay happens automatically, and you don't need to perform any additional decay as such. So next factor is like this data augmentation, and we have seen that introducing wide range of data augmentations in the training helps boost both the baseline and the method you are developing. So the easier data augmentation techniques include this affine augmentations, which include this rotation, scaling, cropping, and flipping. And additionally, we also use elastic deformations or random brightness and contrast changes, which are observed in MR data as such. So the hyperparameters which you will choose for this rotation, scaling, or elastic deformations also depend on the data set. So you might want to evaluate this on some validation data set before you can go ahead for your baseline or the method which you're developing. And in the training, it's also important like how you form the batch. So what we have observed is that in a given batch, the training is quite good if you are able to include all kind of augmentations in any given batch in the training. So here, the first part of the batch would be the random subset of images, which you will sample from the data set. And then the second part would be you only apply affine augmentations on this subset of images which you have selected. And the third part would constitute having this elastic deformations. And the fourth one would be applying this intensity augmentations. And finally, like we also want to apply multiple augmentations on top of each other. And we have seen that using this last part does improve the training and also result in good test scores and also the validation dice scores. Coming to the stopping criteria, as such, it depends like how you want to figure out the checkpoint file which you want to use for the final evaluation. The most common one is like you have a validation volume set and you kind of track the mean dice score on this validation set, and you use the checkpoint file which gives the best validation dice score and during the entire training. And since this is a computationally intensive process, you may not want to evaluate at every iteration. So you might want to compute this periodically after a fixed number of iterations. And coming to the visualization, I think it's also important to track this mean dice value. And we should observe that this goes up during the initial part of the training. And coming finally to reporting these results. So at the test, in the test set and as well as on the validation set, what we want to do is we first want to resample both the image and the mask for whatever resolution we have decided, predefined for the training. And once we get the prediction, we use nearest neighbor interpolation to resample back this predicted mask to its original resolution, and then compute the dice score on this prediction, which is resampled back to its native resolution. And we want to mimic the same behavior on the validation set, what we are doing on the test set. And since this helps in selecting the model which we will use for this evaluation, it's always best that we have the same set of behavior in how we compute or track this dice score both on the validation and test sets. And once you compute this dice score on this test set, it's always important to look beyond the mean values. One way to do this is you also compute the standard deviation. And secondly, you can check all the different volumes, they report different dice values. So you can check with the baseline, which are those specific volumes which give you the improvements. And in addition, like you also want to know the improvements which you have obtained with the given method are significant or not with respect to the baseline. So you perform some kind of statistical significant tests, such as paired t-test or permutation tests. And coming to the tricks, some tricks for the debugging. So whenever like I write any network architecture or something, what I try to do is I take one random 2D image with some foreground labels and try to overfit the network to just this image. And I think this also works across many other problems. So if this overfitting does not work, something is really wrong with the network or some definitions like loss or in the training or the optimizer. I think the idea would be to first fix this before you move to training with many volumes and different batch sizes and trying to figure out all different hyperparameters. And for this visualization, which you will do in the previous part, TensorBoard or weights and biases are your friends. So you would like to track this different train and validation loss. And also you would want to print this each structure which you have in your volumes for the validation set. And you would also want to visualize how the predictions look like. So you can also plot some of these validation images against the ground truths. And like during the training, it might learn to predict different number of foreground structures. So you also want to ensure that they all have similar color maps. So for this, you can use this fixed CMAP range, which is which ensures that the predicted masks have the consistency in the label colors across different images. And lastly, like learning with limited labels is also an issue, especially for medical data sets, because we know that we don't have a lot of annotations as such for, especially from the private data sets, which we get from hospitals. So one way to figure this is using some kind of pre-training mechanism. Instead of assigning random weights, you have some pre-trained network weights, which you can use, especially in such scenarios, as they will help you have a better start point in terms of the training. So there are three different possibilities here. One is using the ImageNet pre-training weights. And secondly, let's say you have trained on a larger data set of the same modality and you're transferring that weights to a local private data set. You could use that same weights as your start point instead of random weights. And when tuning this, we have also observed that one could only tune parameters such as the batch norm, and tuning only these limited number of parameters also kind of gives you pretty good performance instead of tuning all the weights in the network. And the third one is self-supervised learning. So where you can use this unlabeled data images from the data set, and you can apply some kind of contrastive learning or reconstruction loss-based methods to pre-train this network using only the unlabeled set. And the other possibility beyond this pre-training could also be using some kind of semi-supervised learning methods to improve the performance, especially in this limited annotation settings. The first one is, like I mentioned previously, data augmentation, but you could also use some kind of generative models to generate this synthetic image label pairs using both labeled and unlabeled sets. The second one is consistency in prediction. So the idea here is that irrespective of the transformations you apply on the input image, the network prediction should be similar. And this kind of acts as a regularization for your network training. And some articles also suggest that you would want to use like a teacher-student model instead of one fixed network here. I will show you an example of how this architecture might look like. So this is one possible architecture for this having consistency across the predictions. Like as you can see here, you apply two different transformations on the same image, and you can apply the inverse transform on the output prediction, and they should match with each other. Yeah, lastly, also we have this self-training where you use the pseudo labels of the unlabeled data as the proxy ground truths to also improve the training. So this would look something like this, where initially you have a network, you train it with the limited amount of labeled data which you have, and then you infer some pseudo labels for the unlabeled set, and you include this as well in retraining your network. And you can do this process iteratively till you have some kind of convergence in these pseudo labels. So finally, with the post-processing, so we have some kind of tools to also improve the predicted segmentations. The first one is using conditional random fields. And here you have different hyperparameters again, and we need to figure these out using some small validation set. And the second option is to use a denoising autoencoder, which you exclusively train along with your CNN on a noisy segmentation so that it can denoise these segmentations at the test time. And finally, coming to the things which do not fit into the above sections are prominent, especially when you want to train 3D networks. So we want to have some memory efficient training mechanisms. So these reversible blocks are quite popular in this setting, especially when you want to train either a lot of 3D volumes or having a higher batch size for 2D images. Since they do not require to store the activations, these improve the training in terms of how much memory it requires for in a given single GPU. So you can have more volumes in the training. And you can check the link which we have mentioned here to include some of these training blocks. And lastly, we also see a lot of these imbalanced data sets in medical images. For example, one of the example could be this metastasis or lesion segmentation, where in the brain volume, there are hundreds of slices, but you have lesion occurring only in like very few slices, like a single digit number. So when you prepare your batch for the training, you want to ensure that you don't pick all the slices randomly, because that will make sure that most of the batch does not have any slices containing your lesions. So you want to explicitly ensure that you have these slices, at least 1/3 or more in your batch. And again, since this is an imbalanced data set, you want to choose your loss function accordingly, like a dice loss or a focal loss. Thank you for your attention.